Our next speaker is Dennis Wingo, and it's not too late to plug your book, is it?
No, I have a book signing right after this session.
That's terrific. Well, I think Moonrush is a great book, and I hope that you'll take a look at that, because it presents really, I think, a wonderful comprehensive list of reasons of how we can go to the moon and do things. And so with that introduction, Dennis Wingo will tell us about lunar resources.
Unfortunately, I'm going to have to plug in my laptop here. I can answer one of these.
I'm going to hold this one here.
Yeah. I can answer one of those questions that was just asked, that you asked a few minutes ago. The normalized flux in the present time of asteroidal materials on the Earth is about 2,000 tons a day, and just close it. It's a factor of 81 less on the moon, so 2,000 divided by 81 should get you a rough number that you can use. That's the daily flux.
I think the ratio isn't quite that strong. That's the ratio of the mass that's in the area.
Is it mass? Okay, I'm thinking area.
The ratio of the area
Yeah.
plus thermal plus the Earth concentrates a little bit more because it's got more gravity.
Yeah.
It would be more like 16 or 20.
Okay. Well, that's actually more.
Yeah, so you'd get about, say, 5% of the flux on Earth you get on.
Okay, cool.
5%.
Okay, well, I'm just going to dive right in here. Basically, this is a slight update of some of my Moonrush stuff. Lunar resources derived from NIFE impactors and their implications for lunar development. But in order to look at the moon, we have to start out at the Earth. And the fact is that we have always used extraterrestrial platinum group metals. This is a picture of the Sudbury astroblem, which is the remnant of the Sudbury impactor of about 2 billion years ago. And if you look at the little red dots around the edge of the astroblem, those are all platinum group metal mines. There's also nickel mines, all in the Sudbury district here. Footwall project. There's tons of nickel mines here. They have already pulled $100 billion worth of nickel out of the Sudbury astroblem, and they project another $100 billion worth of nickel is still in the ground there. And this has always been a hugely controversial subject. The geologist at first, I forget his name, from the Canadian side, who said this was an astroblem, was basically blackballed for 20 years until they finally figured out that he was right by looking at the ratios of the metals and several other things. And now the Canadian government, yeah, it was their idea all along. I love what Paul said there, because that's typically how it goes. Also, the other 65% of all terrestrial platinum group metals come from this area right here. It's called the Vredefort complex. This is less tightly coupled to platinum group metals, but this is also about a 2 billion year impact. And the Marinsky Reef, which is where all of the platinum group metals come from that are mined in South Africa, is in the upper right of this astroblem. This is another astroblem. Pretoria is kind of down toward the middle here. But right now, southern Africa in this area, there's very little nickel in this area, but it does have the platinum group metals. It's loosely coupled, but another interesting fact is in North America, the Stillwater complex is also loosely coupled to an asteroidal impact. So there is at least the suggestion, and coincidence what, that 3 out of the 5 of the greatest terrestrial sources of platinum group metals are associated with impacts. Now, Paul, being much smarter than I am in terms of all of the science here, the carbonaceous chondrites can have a much higher enrichment in platinum group metals than NIFE impactors. So it's pretty clear that Sudbury is an NIFE impactor, and these others could have been carbonaceous chondrites that also had increased concentrations of PGM. So But it just, to me, is very interesting that 3 out of the 5 areas where we mine platinum group metals in the world are directly associated with asteroid impacts. Lunar platinum group metals derived from M-class and LL chondrite, 40 to 90% iron, 5 to 60% nickel, depending on the taxonomic classification, 0.5 to 6% cobalt, and 10 to 200 parts per million of platinum group metals. These are a representation of the distribution of PGM fractions in the terrestrial meteorite inventory. There's a much larger data set in the paper, a really nice paper by Pietev, Jacobson here. But if you look, these are all in grams per ton or parts per million platinum, ruthenium, iridium, and gold here. And so it varies from about 2 to about 22.8 grams per ton of platinum. And you see the distributions there of the different, and it turns out that, and there's a lot of variability within the NIFE taxonomic classifications, and one of the classifications is this distribution here. And so you can see that there, even though that there are 3% of all impactors are NIFE, that there's a large distribution variation in these valuable metals. But here's where it gets interesting. This is a graph of lunar impact dynamics, and it's not super clear, but the vertical line there with the dots is the average estimated impact velocity, and I'm using the higher number. There's another number that's out there that says the average impact velocity is 14 kilometers a second, but 16 kilometers a second is the high end, and I'm just kind of erring on the conservative side. But if you look, the distribution, the velocity distribution curve there is highly skewed by the smaller number of very high velocity impactors, which are comets, retrograde, but mostly comets. And you have a large number of very low velocity objects on the low side of the velocity distribution curve, and this is very important. Although our friend Harrison Schmidt will say that very little of this material is left on the lunar surface. We'll see one of these days. This is a distribution curve developed by Gerhard Newcomb. There's one small error in it. One of these is 10 to the 10 on the back side. We found this out. We have to fix that. But this is the crater diameter versus frequency in Meritum Culatus, Nubium, and Alphonsus, which is representative of Mari, the Nubium area, and then Alphonsus, which is a highland area. So there's, as you may expect, as you get to smaller objects, there's a lot more of them, and as you get to larger objects, there's much fewer of them. But if you take a look, this is a study done by Elizabeth Pizarro and Jay Malash at, I guess they're University of Arizona, different places where these guys are at. They looked at the Canyon Diablo impactor, and this is where Jay, and they kind of decide on different years, different numbers here, but they looked at a very interesting telltale sign. They looked at the isotopes of nickel 50, the nickel 59 isotope, which is a cosmogenic isotope that when cosmic rays hit an NIFE object, they will create isotope fractions, and that isotope fraction is dependent on depth, as you might expect. And so if you have a lower velocity, and what they found out is by taking a whole bunch of samples from Canyon Diablo, they were able to kind of figure out that about 15% of the Canyon Diablo impactor, which is the black area over here on the far, the contrast isn't as good here, but this black area on the far right is how much of the object did not melt. And that roughly corresponds to the 4,000 to 7,000 tons worth of Canyon Diablo object that has been found over time. And this is how they came up with the number that it's 20 kilometers a second. If the Canyon Diablo impactor had hit at 15 kilometers a second, and this is just based on the materials properties of nickel iron cobalt objects, that about 35% of the object would have survived. And in talking to Elizabetta on the phone, they ran the numbers but didn't publish them. At 10 kilometers a second, 65% of the object would have survived. And that is important because if you look back you'll see the average velocity is 16 kilometers a second. So on this side of the curve, there's going to be a lot of objects that not just the blasted, very small sized particles will survive. So I'll go back here. M-class impactor survivability, they melt at pressures above 271 gigapascals. If Canyon Diablo hit at about 20 kilometers a second, 15% fragmented with no melt, and just what I was saying there, there is a lot of M-class objects that could have hit and survived in some kind of fragmented form. This is a probabilities. We know that about 3% of all inner solar system objects, at least in the current era, and this probably translates back through time for a good ways as well. About 3% are impactors, and based on Dr. Newcomb's graph, it's about 10,000 craters per million square kilometers. Mare Nubium about 14,000, and in Alphonsus it's about 25,000, and that's out of a total lunar surface area of 38 million square kilometers. The Mare is about 19% of the lunar surface, so that translates out to about 86,400 craters of one in the Mare, which, and this is 1 kilometer craters or greater, and that works out, 3% of that's about 2,500, 2,600 NIFE impactors, craters 1 kilometer or larger, which is comparable to the Behringer impactor. There's about 845,000 in the non-Mare regions, which represents about 25,000 impactors. And the Canyon Diablo fits this size at about 100,000 metric tons minimum. So that means that theoretically somewhere between, being very conservative, 1 to 10,000 kilos of platinum plus similar amount of iridium per object. And all of it's not going to be there. There's loss mechanisms, and I'll show that here. In the statistics, there's on the lunar surface about 28,000 total impactors. NIFE being very conservative, average impact velocity 14 to 16 kilometers a second, 15 to 63% material survival. That can be less because some of it is blasted back out into space. There's about 1,300 10-kilometer craters on the lunar surface, so about 39 of those are NIFE. About 100 kilometers craters on the moon, which means about 3 NIFE impactors. So if you run the numbers, total resource base of about 140 to 590 billion tons of NIFE, depending on what the loss mechanism is, or 3.9 to 16 billion kilos of platinum group metals. And on the Earth, our total known platinum group metal inventory is about 120 million kilos. So that tells you how much more is probably on the moon. Mitigating factors, some of it's blasted off, an additional, but there's also on the other side an additional 1% of all the impactors are stony iron. LL chondrites with very high platinum group metal concentrations are also on the lunar surface, and there's about 1% of all impactors are LL chondrites. But LL chondrites have less material strength. So there's all these different factors that go in here. So we ran all the numbers. So we're, again, another estimate about 77 billion kilos of platinum group metals on the Earth, and that's 1,000 times the Earth reserves. And this is a hypothesis, and like any hypothesis, what are some of the tests? Infrared experiment, an orbital experiment with high resolution should be able to, at the very limb of the moon, when the moon is going from sunlight into darkness, since the thermal emissivity of NIFE is so much higher than the lunar surface itself. You should be able to see this in the IR. You should be able to see it with high resolution, high power radar because of the much greater reflectivity of these objects, because I'm thinking chunks. We already know from the Apollo era data that between 0.1 to 1% of all regolith is NIFE fragments. We already know this from Apollo. So there's your lower band right there. And I kid Harrison Schmidt about this because that means there's about 10,000 times more platinum group metals in just the regolith than there is helium-3. I went and did a literature search, helped a lot by my professor at the University of Alabama, Huntsville, Dr. Chuck Lundquist, who's one of the original founders of the Lunar Science Working Group. There are papers there. L.L. Hood has a good paper, and they talk about Reiner Gamma. This is an old paper that they had back then. It is a very large, interesting magnetic anomaly on the lunar surface that is not associated with an antipodal impact. It's 30 by 60 kilometers. The lunar orbiter 4 resolution, about 1 to 5 meters. There's no vertical relief of the Reiner Gamma area, and that lack of discoloration there is because there's a mini magnetosphere over this site. And that is what deflects the solar wind. And one of the theories on lunar surface coloration is that it's solar wind radiation damage, basically, of the lunar surface. If you have a mini magnetosphere here, then that blocks the solar wind from impacting the surface. And they actually proved this on Apollo 16 because the Apollo 16 landing site is within the edge of another anomaly, the Descartes anomaly, where there's also a high magnetic field strength. Here's an overlay of the magnetic B field over the Reiner Gamma site from Apollo 16 data. This is data from the Apollo 16 subsatellite that as they went over the area a multiplicity of times. And this is a map that was derived from that because Apollo 16, the gravity subsatellite, had a magnetometer and it was in a low equatorial orbit. So this is the B field of the lunar surface at the equatorial region, and the highest B field is over there, and that's Reiner Gamma on the far left. And there is no known, there's a couple of possible explanations for Reiner Gamma, but there's still a lot of controversy. And if you look, these are B field plots from actual data, and then some of these are B field models, and they have the magnetization orders of magnitude. It's very high magnetization in this area. Hood in 2002, that data there was from the 1960s, and Hood, in one of his possible explanations, is saying, well, it could be a buried nickel-iron impactor. But even as late as 2002, at the workshop on the moon, Reiner Gamma is a major unresolved anomaly needing further orbital and in situ study. And this is a picture of the same area from Clementine.
Oh, TMA1, like in 2001.
Yeah. This is more data from Apollo 11. This is a stony iron fragment, 2 millimeters in diameter, with a fragment of NIFE. Metal meteorites on Mars, both Spirit and Opportunity have found metal meteorites. There's contrast isn't real good, but you can see both of them. The one that Spirit found is on the lower right, but also you can't really see it, but in the lower left, there's almost buried NIFE as well. Both rovers found that within their very limited areas that they've traveled. So that means that nickel iron fragments like this are almost ubiquitous on the surface of Mars, leading to the conclusion that there is a nice ISRU resource on Mars, because the Opportunity, that fragment right there, they're estimating that's about 80 kilos. If you took that and melted it and used it as shielding, you'd get about half an inch of shielding over a really nice area for a habitat. So these are resources we know are on Mars, and we know that are on the moon at the worst case. Now, what Harrison Schmidt, we always have this back and forward here, he keeps saying, well, the atmosphere is a great decelerator of these objects. But the Canyon Diablo impactor at worst case hit at 15 kilometers a second. Is that slow? That's not real slow to me. And I kid him about it. So we go remote sensing experiments, 13 to 70 centimeter radar, infrared at 1 to 3 micron, can test these locations. You have to have the radar to look at Reiner gamma if it's a buried object. The infrared will only find surface materials. Now, here's the historical supply and demand of platinum on Earth, because we want to, as I say in my book, we go to Mars to take our civilization there. We go to the moon to help save our civilization here. One of the reasons to go to the moon is for resources. And this is the demand curve for the past 20, 30 years on the Earth. If we're going to go to the hydrogen economy, this will multiply. Right here, just the blue curve is fuel cell stack, the increase in demand between now and the year 2050. 25 million ounces per year, and the fact is we do not have enough platinum group metals on the Earth to convert all of our automobiles to fuel cells. Here's the demand curve, different scenarios of penetration, and how much it's going to cost. Right now, a fuel cell stack uses about 2 ounces of platinum. The UK government projects that they'll be able to get this down to 0.2 to 1 ounce. We'll see. Platinum group metals provide an industrial rationale beyond science for the lunar return that connects to the hydrogen economy. If we do not connect lunar exploration and development to concrete improvements in our life here on Earth, it's not sustainable. It's like we were at NASA headquarters the other day. The wind's blowing in one direction today. What happens in 2009 when the wind might blow in another direction? We start small and bootstrap. PGM buried metals can be found fairly easy via remote sensing. The regolith in many areas is already rich in it. So anytime you're processing regolith, you can get platinum group metals out of it, or you can get metals out of it to help with your lunar outpost development. This is kind of unfortunately it's not showing up too good, a lunar induction furnace that we came up with. I did a study for NASA Langley of a modified ESAS outpost buildup scenario that included commercial enterprise. And we take the LSAM descent stages and we use those to store liquid oxygen. You can store 60 metric tons of liquid oxygen in a spent LSAM descent stage. Which makes instead of wasting these LSAMs, which we're talking about now, you can fill them up with liquid oxygen, and there's your propellant farm. And if Paul's right and the water's there, you can stick hydrogen in there. And Gordon Woodcock and I ran the numbers. A LSAM descent stage is a lunar single stage to orbit, able to deliver 25 tons of payload to lunar orbit, and be able to return back to the surface empty. So talk about single stage to orbit, NASA's already designing it for the moon. And then over here you have commercial payloads, and what you want to do on the moon is go to being able to process metals as quickly as you can. And Ed McCullough from Boeing has got some great ideas on magma electrolysis and getting metals out. This is some of the stuff we did just starting out very, very easily. This is a Lotran view. We've got the Lotran rover and a lightweight crane that's being developed by NASA Langley for picking up payloads and dropping them off. ISRU metals processor. Lunar uses of M-class asteroidal products, large-scale radiation-safe habitats. 3 feet of metal gets you the same protection as the entire Earth's atmosphere. There's a lot of our waste material from getting platinum group metals is an incredible resource for use on the lunar surface. You basically have stainless steel, which is nickel. It's Inconel, an Inconel-like iron alloy, nickel iron alloy, for rovers, building a railroad, a lunar railroad. You can even, if you use straight iron, it's more lossy than aluminum, but you can actually send electricity, and the lunar surface is so electrically non-conductive that you could lay these rails out, and you could have maglev, and you send the power through the rails. because you don't have any electrical problems with grounding. I mean, grounding is actually a problem on the moon, and so you could send the power down the rails, and it would be fairly easy, especially if the iron is as ubiquitous as we think it may be. Just think habitats, think living area with big iron structures or nickel iron structures, Inconel structures, building industrial machinery, rocket engines. Today they use exotic materials, but just think there's a lot of iridium in this. You keep the iridium on the moon and you can make reusable rocket engines, because iridium is a very, very high temperature melting material. So you could do that. Just all kinds of cool stuff that you can have. This is kind of our notional lunar base with your metals processor there, and you're building big structures and frames, and it just really, and the point has to be emphasized that ISRU, if we don't go to the moon and do ISRU, we might as well not go, because all it is a science fair, and the American people aren't going to support us. A $3 billion a year science fair program. And that's basically my presentation.
Thank you. Good question.
Yes, sir.
2 years ago, I went to the Planetary and Terrestrial Sciences Symposium in Sudbury.
Yes, sir.
With the same fascination, where did this stuff come from? And I talked to the geologists at North Korea, and their response at first shattered, what I was looking for. But now I look at it like they are totally convinced that the nickel, copper, and other wealth did not come from the impactor, but that the impactor struck at such a velocity that it shattered the crust, and the magma below came up through the cracks, and that's where they're finding it, in the cracks in the crater rim. And at first I had thought, well, if there's some way to detect what's unique about Sudbury orbit, maybe we can find craters on the moon that might be future Sudburys. That idea went down the tubes. Now you're looking at lower impact incidents, or maybe we should be looking for high impact incidents in areas where the crust might have been thin enough, and where it was early enough that below there's still magma, and the magma contains these elements, and again we would have
well, the response is, and I understand, and I've read the same things, but if you take a look, what volcano on this entire planet also puts out $100 billion quantities of nickel, which is the same magma pools from under the surface? There would have to be a very, very unique magma pool under that part of Canada that just happened to have $300 billion worth of nickel. It seems to be kind of defiant, because we've never ever seen any volcano on this earth that has had a concentration of metals directly. You always see like gold and all, but they're in the cracks, so that makes sense. But also the platinum group metals, since they always travel along with the nickel, it seems to reason that, yes, and you're going to get melting. And 2 billion years ago, the crust was thinner. This was a big object that hit. And yes, there had to be some, but I would contend that the magma came up and just basically melted the object. And because I think it is very, very interesting, and you see, because you can tell the cracks, it's right along the edge of the astroblim, where you have all of the, but also if you melted the object, there would tend to be some differentiation from the melting event as well. So that would be my response to that contention, because if you look at the history of the whole thing, they were dragged kicking and screaming even into the concept that it was an impactor.
Dennis, you mentioned remote sensing, and Are there, to your best of your knowledge, any of the suite of instruments on Chang'e or?
Well,
Chandrayaan?
Paul and I have had this discussion, and I've talked to the guys at Raytheon that are building the instrument. They're trying to do things that may help that. I think if the mini RF flies on LRO, since it has the higher resolution, it might be able to. But Paul had a very interesting picture in his presentation that showed an ejecta blanket around one crater that looked completely different than all the other ejecta blankets. And if you look, any kind of radar response from an area that's enriched in iron is going to have much higher reflectivity than just a normal one. So there's at least the possibility that ejecta blanket around that one crater is showing you metal, because that's what you would expect to see.
Did you run that by Paul?
No, I just saw that, and I hadn't had a chance to talk to him. And this is something that he and I will discuss offline, where we can go back and forth. Yes, sir, Hugh.
Yeah. About 30 years ago, Kraft Jerry made a personal study of the materials that mankind would be running out of first on Earth.
Yep.
It concluded with tungsten was going to become very critical, very expensive.
Yes, sir.
Can you tell us about the availability of tungsten?
Very, very little. I don't think any sample has had any more than nanogram of something like tungsten. One thing that was very interesting, though, I actually have on my desk a 15 kilo, what is it? It's one from South America. I forget the name of it right now. There's 200 grams a ton of germanium and 86 grams a ton of gallium in that impactor. So what you see is, you can't think of nickel iron impactors as homogeneously having ratio X of iron, ratio Y of nickel, ratio Z of cobalt, and then various ratios of just the platinum group metals. You get other very interesting and valuable metals, like if you're going to make high efficiency solar cells, gallium and germanium are incredibly important to the semiconductor industry, and they're getting more expensive on the Earth. So I don't know about tungsten, but I think there's a heck of a lot of interesting, and I think probably even copper, because I've seen a couple of NIFE impactors that had some copper in them as well, which I think is very interesting.
What you're saying is impactors are more likely highly variable in material content.
That is correct. And I think that is incredibly interesting, because recently, I used to think 216 Cleopatra was the biggest one. 216 Cleopatra is 80 kilometers by 200 kilometers by 100 kilometers in diameter, but there's another one, I forget the name of it, I think it's Pisces or something like that, that's almost a 200 kilometer in diameter chunk of nickel iron in the main belt. And 3554 Amun that John Lewis talks about, that's a near-Earth object, $30 trillion worth of material. $30 trillion. Anybody who says we have problems with resources is not looking up into the sky.
Was that his mining of the sky?
Yeah, mining, and I totally recommend everybody read Rain of Iron and Ice and Mining the Sky from John Lewis. Incredibly good books on the same subject. Thank you very much.